So I'm going to tell you a little bit today about work that I've been doing on black hole growth, about black holes feed, and how black holes feed. You can probably see already I'm kind of giving the game away of the sort of three main methods by which black holes grow in this first slide, but I'm going to go into a little bit more detail about how we find these black holes, how we see them grow, and the physics behind it a little bit. And feel free to stop me with questions as I go through. So if you look up at the night sky, then you'll see basically the sky is full of galaxies. And actually along the plane of our own Milky Way galaxy, it's full of stars, but as you move further and further away, then you find that really the stars kind of peter out and the galaxies start to dominate. And this is an image from the Hubble telescope with the Hubble Ultra Deep Field. It's the size of a grain of sand held at arm's length on the sky, and it contains a few thousand galaxies and just a small handful of stars. You can tell the stars by these little kind of diffraction spikes here, but these are most of the galaxies. Even the brightest stars in this image are too faint to be seen by the naked eye, and so what you're really seeing here is just a piece of empty space the size of a grain of sand held at arm's length. And this isn't a unique part of the universe. Everywhere you look on the sky is full of galaxies. And of course, this is an optical image. It's an image that was taken with the Hubble, and you can see nearby galaxies, you can see more distant galaxies, you can see big galaxies and small galaxies. And disentangling this and probing back towards the beginning of the evolution of the universe is kind of challenging. It keeps a lot of people busy. But for reference, this is what the sky looks like all over the place. There are hundreds of billions of stars in our Milky Way, and there are hundreds of billions of galaxies in the observable universe. But I want to talk a little bit today about radio observations. I'll talk about optical and X-ray and about other wavelengths that we use as well to understand our universe. But I'm going to talk a little bit about radio. Some of you probably have one of these on the side of your house. It's the radio antenna. It picks up radio signals, obviously, from the TV satellites that are being beamed down. But as astronomers, we also use radio dishes to do radio imaging. And people tend to think of radio as being sort of something that you're listening to, or in the case of your TV, obviously, this is the data being transmitted down from the satellite. But I think a good analogy for what we're doing as astronomers, well, at one level, it's kind of like radar, and actually astronomers do radar imaging where they bounce pulses of radio waves off things in our solar system, like asteroids and planets, and to map the surface, in the same way that an air traffic controller will bounce radar off planes to see where the planes are. But a lot of the more distant objects, you can't bounce the radio waves off them, but fortunately they're transmitting radio waves to us. And like transponders on planes around an airport, those signals from these objects are telling us about the objects, where they are, and what they're doing, essentially, just like planes. And so, by studying the radio light that these stars and galaxies and other objects emit, then we can tell about their characteristics in the same way as by studying the optical light that galaxies emit, we can study their characteristics too. One of the advantages that we have in the radio is that we can build arrays of these dishes. This is the very large array in New Mexico, ALMA down in South America, CAMA, a telescope that UC Berkeley is actively involved in, is in the Inyo Mountains, just east of Bishop. And then this sort of funny-looking thing here that really looks like kind of wires standing in a muddy field is the LOFAR telescope in the Netherlands, which is made of wires standing in a muddy field on top of them. And so you can get a lot of collecting area basically by combining signals from multiple telescopes. And actually this telescope is spread out all across Northern Europe. It's kind of a new design that's basically replacing a lot of the steel here in these kind of telescopes with silicon. In other words, we're using supercomputers at the back end to combine the signals from really pretty simple telescopes that actually look like some of the first radio telescopes that were built in the middle of the last century. So what do we see when we look at the sky in radio images? Well, here's an image that was made with the Allen telescope array, which I'm going to tell you a little bit about later. There is the full moon to scale, and here is this map of the radio sky. Actually, I'm lying to you. That's the full moon to scale. This is a huge area of the sky. It's 700 square degrees. The full moon is about a quarter of a square degree on the sky. And you're seeing about 4,000 little black dots in here, which don't look very exciting when you compare them to Hubble Ultra Deep Field, right? And which image would you rather have on your wall? All this. But if I tell you that each of these dots is an actively feeding and growing black hole, then the information that's behind that makes it kind of a cooler picture, I think. I mean, not necessarily cooler than the Hubble, but it's still, okay, that's kind of neat. 700 square degrees and thousands of black holes, supermassive black holes, billions of times the mass of the sun that are actively feeding. So, here's a simulation. This is a backdrop of the Milky Way with what you would see if you were 600 kilometers away from a black hole with 10 times the mass of the sun. And it's distorting the image of the background. It's actually warping space-time around it. And you see here the event horizon beyond which no light can escape. I will say I'm not kind of a theorist of the physics of black holes and what goes on beyond the event horizon and all this kind of stuff. I can speak to that maybe a little bit if there are questions, but really that's kind of pretty hardcore, you know, general relativity, and I'm sort of an observer and somebody who studies the phenomena related to black holes, and I'm kind of more interested in what happens to stuff before it falls in and goes over the event horizon. So this is a 10 solar mass black hole in this simulation. These kind of masses of black holes are the endpoint of the lives of massive stars, which will explode as very violent supernovae or as gamma ray bursts, and then they collapse down to form this singularity in space surrounded by an event horizon that kind of veils what's going on really down there at the center. There are also supermassive black holes that I alluded to that live at the centers of galaxies that are millions or even billions or tens of billions of times the mass of the sun. It's actually still an open question as to how they initially formed, but we do see how they grow and how they got up to those kind of massive sizes, and that's essentially what I'm going to talk about. Yeah?
Is that a picture, is that a cross-section?
This is a real picture in the background, but then it's a simulation of what the black hole would do to the background image. So.
That pink area around it is flat.
Well, I mean, this is just, it's a 3D thing in space, but it's warping space-time around it. And
but it's not like a board, it's like a plane.
It's complicated. The space, I mean, you can write down the equations of the space-time, basically. You could move around this thing and still see sort of similar kind of effects. There are actually simulations on this guy's webpage, Andrew Hamilton, no relation to the founding father, but as far as I know. But you can see his simulations of how it would look like to fall into a black hole, how it would look like if you were orbiting around it, and there's some really kind of freaky things that go on in terms of sort of these optical effects, basically, as the light's getting bent by the curved space-time. But this is, you know, this is really close to black hole. This is 600 kilometers away. I mean, you know, that's a short drive, basically, and we never get really this close to black holes, and so making this kind of image is really impossible with the current technology that we have.
So we have a massive black hole at the center of our galaxy, but do we have any idea how many non-massive black holes we have in our galaxy?
That's a good question. We know certainly of a couple of dozen of them that are pretty definitely black holes. We infer that there must be at least thousands of them, probably actually millions. If you look at the sort of the number of massive stars in the galaxy and the number of those that have died over the history of the galaxy, then millions or even billions. But it's a number that's not well known, primarily because these things are just hard to find, and most of them are just floating through space, not really doing very much. So it's the ones that are growing that are actually accreting matter, which I'm going to get onto in a second, that we can obviously see. So having said that you can't really get that close to a black hole, or you could do, but space is really big, and so to get this close to one is challenging, and we don't have the kind of resolution to image them in this kind of detail. How do we find them? And one of the ways, and again, this is what I'm going to concentrate on, is we find them as they're feeding. And an analogy that I've used for how we see feeding black holes is someone who you'll all be familiar with. And of course, Cookie Monster's a puppet, so he doesn't actually eat any of the cookie. The cookie's just flying all over the place. The black holes eat about 10% of what we throw in there, but the rest of it is just, you know, they're messy eaters, basically. The stuff is flying all over the place, and that's how we see them. We see the stuff that doesn't go in, basically. So these feeding monsters I mentioned are at the centers of galaxies. The one at the center of our own galaxy isn't feeding this dramatically, but we do see many of them that are, with hot gas that's spiraling around in what we call an accretion disk, and it's connecting in a way that is not still really fully understood to these jets that are shooting out at close to the speed of light. Jets of particles, they may be electrons and protons, or they may be electrons and positrons, we don't even really know that yet, but these are shooting out into intergalactic space. And these are some of the most dramatic and energetic processes that we see in the universe. But you'll see here, all this gas swirling around, this kind of little cartoon movie here from some guys at NASA Goddard Space Flight Center. What we tend to get actually when we make these observations, sorry.
So there's kind of a strange thing in that animation, I guess.
Mm-hmm.
I mean, it looks like it sinks in sort of in the middle. Can that be real, or is that...
Yeah, I mean, there's an edge to the disk, basically. Again, it's pretty complicated and not entirely fully understood how this infalling material connects into the jet. But yeah, there's sort of a less stable orbit, basically, where stuff can no longer even just...
But I mean, presumably, if you were looking at it from the bottom side, you'd see the same thing.
Yeah.
So that looks like there's something sinking in.
Yeah, well, the disk kind of tapers off, and stuff is going into the black hole, and stuff is flowing out in these jets. So this material, I mean, a lot of it is it's going around on, fairly stable orbits here, but it's losing energy as it does so through friction and through heating and through emitting a lot of light, and that's why it's kind of spiraling in. And then some of it goes in, as I say, and some of it gets shot out. There's another question, just... But what we're seeing here, so here's the little cartoon movie, but what we see when we make these observations is just a snapshot. And here's a snapshot that I took on the drive up to the Allen Telescope Array, which again I'll introduce in a little bit, which is just north of Lassen National Park. And if you want to study how trees grow in the forest, one option is to send a grad student out there with a clipboard and tell them to report back in 50 years. But it's kind of hard to get people to devote that amount of their life to studying some of these kind of long processes. So you can just take a snapshot and say, okay, well, first of all, we need to classify these trees and these trees and those trees, and make sure that we understand that these are two different kinds of trees and that we're not seeing some kind of process by which these turn into those. We can tell that these ones are more distant, actually through the intervening absorption from the atmosphere, and we can do that in space as well, with absorption from gas that's in between us and the object that we're studying. And so we can tell that, these are probably the same size as these trees in the foreground, and again, kind of classifying and then coming up with sort of statistics of how many trees of different sizes we see, looking on the forest floor and seeing the little acorns and the pine cones and studying how this all grows. You can put together a consistent picture just from a snapshot. And really, astronomy's been a lot about snapshots for really thousands of years. Here's a picture of the universe as it was understood kind of around the middle of the 16th century. This was sort of a little bit later than really the beginning of the revolution in astronomy that took place, but we still have here in this frontispiece from a book from 1588, the Earth at the center with the planets moving around on these spheres, the fixed outer sphere of the stars here just kind of rotating serenely about, and of course Queen Elizabeth presiding over the whole affair. Actually, a few years before that, I guess the news was kind of slow to get to England, but Copernicus had already proposed the sun at the center of the solar system with the planets orbiting around it here in 1543 in his book on the revolution of the heavenly spheres, and this was the beginning of the heliocentric universe, but still everything is kind of moving around pretty serenely, and the stars are out here just kind of coasting in their orbits. But in 1573, Tycho Brahe observed a new star that appeared in his observations. I think it's I here in this plot. And there was another supernova that was observed. So these are the explosive deaths of massive stars. Typically, there's another supernova that was observed by Kepler a few years later. And this was the real understanding that the sky changes in the Western world, at least. I'll mention, I know we have some visitors from China here, and actually the Chinese were onto this hundreds of years before the Europeans were, looking at observations of guest stars. And actually some of you, I'm going to show a little excerpt from a Chinese chronicle later, and I always ask if anyone reads 11th century Chinese, maybe some of you do, but I'll get to that in a few minutes. But in the West, really, this was the beginning of sort of the revolution in our understanding of how the sky changes. So our nearest supermassive black hole is at the center of our own galaxy, and these are some observations from a group down at UCLA, made with the Keck telescopes, and these are real images showing the orbits of stars around some object that's just marked here with a star in this plot. The object itself isn't seen here. I'm going to go back and run this again. And so these are stars whose motions have been studied from 1996. You can see the year kind of ticking over here up until the present day. I think this one goes up to 2011. And you see some of the stars kind of coasting in on fairly wide orbits, but some of you will probably have noticed there was this star that came in here and really had a kind of dramatic turnaround and was shot back out again in the opposite direction. I mean, imagine what it takes to stop a star in its tracks and turn it around and fire it back out again. Okay? What could possibly be lurking here at the center? Well, we're pretty sure it's a 4 million solar mass black hole that's at the center of the galaxy. Yeah.
Maybe this one, Brian, I didn't hear, but what was the time frame for that real sharp, like we were just describing?
A few months, I think. Maybe a year. I mean, the whole orbit there is kind of 15 years, something like that. And it gets fairly close. I mean, it doesn't get close enough to be disrupted by the black hole. It just gets kind of turned around and shot back out. So the black hole at the center of our own galaxy isn't actively feeding right now, although there's a gas cloud that's been falling in that some of you may have read about in the media that's kind of exciting some interest and may actually give rise to increased activity from the black hole at some point. But a lot of the work that I'm doing is on these much more active galactic nuclei, as we call them, or AGNs. You may hear me use that term. Where the black hole at the center is surrounded by the accretion disk that you saw earlier, and then this big kind of donut-shaped torus of gas and dust. And actually this little cartoon, this is actually from a research paper, so it's showing kind of the various kinds of things that you may see if you were looking at this black hole from different angles. It's kind of like the story of the blindfolded man trying to touch the elephant and figure out, touch the legs, it's a tree trunk, touch the tail, it's a rope, touch the trunk, it's a snake. And we see these objects from different directions, and they look like quite different things depending on whether we're looking down the beam of this jet that's shooting straight towards us, or whether we're seeing from the side here a lot of gas and dust that's obscuring our view of the central region, or whether we're viewing from different angles, and then whether or not, in fact, the black hole has these jets shooting out or not. And we still don't, as I say, really understand exactly what the phenomena are that lead to jets or no jets. Yeah.
So on that side there on the left, it says radio loud above the line of
Right.
axis and radio quiet.
Right.
Why would that?
So this isn't the same object. This is kind of a cartoon of, you know, looking on this side, a black hole launching jets, looking on the other side, a black hole that's not. And different kinds of things that are seen: Cepheid galaxies, quasars, broad and narrow line radio galaxies, optically violent variables, BL-like objects. I mean, all of these things are things that were classified by astronomers. And again, I said, you know, classification is important, but we're understanding now that all of these different things are actually just manifestations of really kind of the same fundamental process that's going on here. Yes?
You mentioned that when the black hole is feeding, 10% of what goes in gets eaten up or whatever. Now, is the jet going out, is that the 90% that doesn't go in, or is that the 10% that comes in and goes back out?
None of the stuff that actually goes in over the event horizon comes back out, at least not on any kind of reasonable timescale. So the jet is carrying some of that away. There's also probably winds of gas that are coming off this accretion disk that's falling in. Yeah, I mean, there's only a small amount that's actually making it in there, and the rest gets out one way or another eventually, basically, yeah.
What causes the jet to go in two directions only?
I mean, essentially, it's kind of, there are magnetic fields in the disk that are getting wrapped around and twisted up, and it's kind of like twisting a rope, basically. It sort of, the magnetic fields, as they're twisting around, basically collimate, in other words, kind of focus that jet. And it's sort of shooting out like a fire hose, basically, along the axis of rotation of the black hole. So the black hole at the center here is likely spinning, at least, you know, it's probably unlikely that it's just completely static relative to the accretion disk, so it's spinning around and that's kind of forcing some of that material out.
And how far does it shoot out?
I'll show you in the next picture. Yeah.
There's something that I'm not understanding. It seems pretty peculiar about that 90% number. And if you take that massive black hole in the center of our galaxy and that star that whipped around it, would that mass be considered something that was feeding on it and shot back out?
Not really. I mean, what I'm talking about here is, really a different phenomenon in terms of the black hole at the center of our galaxy is not really feeding very much at all. This is kind of orders of magnitude different in terms of the amount of stuff that's flowing in, basically. This big disk structure, we don't see, certainly on this scale, in our own galaxy.
But what I'm trying to get at is, how do you decide what to put in that material that you decided the black hole was really feeding on versus other material that's just kind of orbiting in the area of the black hole?
Well, because we see, in these real active galactic nuclei, I'll move on to the next picture and show you, because you'll see kind of how, comparing to our own galaxy, how different this is, yeah.
Why isn't there a black hole?
Very good question, something that we're trying to understand. I mean, actually, probably most of them aren't. Space is very big, and getting gas in to those central regions is kind of hard. But, yeah, actually our black hole is less active than we think it really ought to be, given its size, and that's a bit of a puzzle. So, again, showing sort of the power of observations at different wavelengths. Here's X-ray observations from the Chandra Observatory in space. Here's a visible light picture from the Hubble Space Telescope, and here are radio observations from the Very Large Array that I showed you earlier. And then you combine them all into one image here, and you see the central galaxy here. So this is probably hundreds of thousands of light years across. It's got a black hole at the center. There's some hot gas at a couple of millions of degrees that's glowing in X-ray light here. And then there are these radio jets that are shooting out from the central black hole here again, sort of initially close to the speed of light, and sort of propagating out like bubbles basically through this hot gas out, essentially millions of light years out into intergalactic space. So these are hugely powerful engines that are, shooting out these jets that are then actually, you can see sort of faintly here, these little cavities in the X-ray gas, and so the expanding bubbles of these radio lobes are sort of excavating holes in this gas on intergalactic scales. So there's nothing like that going on in our own Milky Way, at least right now. These are massive objects. This is more common in the distant and hence the early universe, sort of closer to the Big Bang, when galaxies were more active than they are today, and we can sort of talk a little bit about why that is too. So you're seeing really what I would call negative feedback here. Basically, the black hole is sort of blowing away material. It's blowing bubbles into the surrounding gas, which otherwise might be falling in and accreting onto the black hole. And so the black hole is sort of regulating its own growth, essentially, by sort of stopping some of this fuel from ever making it down into the central regions. And this is realized now to be, for at least around the last decade, this has been realized to be an important part of the formation of galaxies themselves. Here's a rich galaxy cluster in the local universe, hundreds of galaxies here that are all kind of living in a very dense environment. So this is a little bit unrepresentative. The whole universe is not like this, but there are a lot of galaxies that live in clusters. And you see certainly a lot of these massive galaxies, well, they look kind of orange in this picture, or they're red and dead, basically, in sort of the parlance of astronomers. Some of you who were here for Mariska Creek's talk last month will have heard her talk about how galaxies grow and how they evolve. And so, there's a lot of big red galaxies, and there's some fainter blue galaxies, but there aren't really very many big blue galaxies. But if you put gas into simulations, into supercomputer simulations, and you just evolve it forward, you should get these big blue galaxies too. You should get big blue galaxies and big red galaxies. And it was only with the work of Darren Croton, who was at Berkeley at the time, and others, Phil Hopkins, who's still here, and some other researchers, that have realized the role of these active galactic nuclei in cutting off the accretion of that gas, that we've realized why, in this plot on the right here, where you're seeing mass increasing to the right, massive galaxies over here, less massive galaxies over here, and then you're seeing red galaxies at the top and blue galaxies at the bottom, and again color-coded as elliptical galaxies and as spirals here. So there's red ellipticals and blue spirals, but essentially this is what you see in the simulations before you turn on these active galaxies, and you'll see in the top plot here, basically the big blue galaxies go away in the simulation, and this in fact matches what we see in the universe, that those black holes that are blowing the gas away as they're feeding are also truncating the formation of stars in their parent galaxy too. So they're sort of regulating the growth of the black hole and the galaxy itself. There's some more work that's been done, including with some observations that I took up at Lick Observatory down in the South Bay. Again, the Very Large Array Radio Telescope comes into play here, so the background image is optical light. You see a couple of galaxies colliding here. There's another galaxy over here, and two of them here have these AGNs, these actively feeding supermassive black holes in there, and are shooting out jets into intergalactic space, which are kind of splashing off surrounding gas basically here. But this one's kind of interesting, because we have a little blue blob here, and this is neutral hydrogen gas, again seen in radio observations, and at the leading edge here you see this little blue glow, which is about 10 million new stars. They're all kind of under 6 or 7 million years old that are being born in the system as the jet from this nearby galaxy is slamming into the gas and actually creating shock waves that are triggering gas clouds to collapse. And so this is what I would call positive feedback. It's also been seen in the more distant universe here, again with jets in the kind of contour pictures here, and then a negative image in optical light basically showing where the new stars are forming, and they align with the jets that are spreading out from the black hole that's here at the center in this object. And so positive feedback and negative feedback kind of working together, you get a balance which is thought to explain this sort of long-standing puzzle about why big supermassive black holes live in the most massive galaxies and why the smaller supermassive black holes live in less massive galaxies. Essentially that there's somehow this thing that's sort of the size of our own solar system, but millions or billions of solar masses that's living at the center of the galaxy knows about things that are going on galaxy-wide scales. And obviously the connection, again, there is through these jets that are going out and doing work basically on the surrounding gas. But snapshots miss the action. So, I showed you this picture before, and I said, you could go out there and look at the trees and basically figure out, a little bit certainly about things on the lifespan of trees in the forest. But, what if something pops up just in one of your observations and then it's gone again, and you're thinking, wait a minute, what was that? We want more detail, we want more time resolution, and we want to figure out, was that something real? Was it something that's important in the life of the forest, or was it just some kind of crazy fluke? So snapshots miss the action, and I would say, even snapshots taken a while apart. So here is a view of my hometown in the UK, the little town called Haswell, in, I guess, the early 20th century. And here's a picture of it in the modern day. I'm kidding. Here's a picture of it in the modern day. So you can actually see the same trees here. You can see things that are kind of evolving over time. You can see the cars have changed. But really, if you want to know about kind of the daily habits of people in the town, then you do need to kind of sit there and watch for a bit on the kind of time scales of events that are taking place that are of interest. So on to the Chinese chronicles. Does this look legible to any of you guys there? So this is in 1006, some observations were made of a guest star that appeared, and actually it was very precisely described as to where that guest star was. It took about 339 years to publish those observations. We try and publish things on a shorter time scale, but this is from a 14th century chronicle. And then it took another 620 years to get the follow-up observations, and again, we try and be a bit quicker than that. But here, the 1,000-year timescale is interesting, because here's supernova 1006, seen about 1,000 years later, with the Chandra telescope that I mentioned already, with some optical telescopes in Hawaii, and with the radio telescopes, the Very Large Array, and the Green Bank telescope. And you see this shell of hot gas that's expanding out into surrounding space. Again, kind of a shock wave coming out here. And we can study a lot about the lifespan and the process of supernova explosions by sort of targeting our observations onto those timescales. Yeah?
You didn't catch me when I first was pointing, but there was a slide where you showed 0 and then 1 million and 1 billion. Mm-hmm. So your English heritage is showing, because that's an American trillion.
Oh, well, no, I think that's an American billion, actually.
The scale is not right.
Well, it's a log scale. It's a cartoon, you could pull out the original plot from a paper and see that sort of more accurately. Yeah.
What's the white business on the other side of that?
This thing?
Yeah.
I guess that's part of the shockwave. I mean, I'm not a supernova expert. I'm showing this to sort of just talk a little bit about the timescales of transient and variable sources. And, to talk about transients, there's actually been some work, particularly with the SWIFT satellite, in the past few years that's really been kind of revolutionizing our understanding of the transient sky at high energies, particularly in X-rays and gamma rays. So what kind of things do we see in the transient sky? What kind of things pop up and then go away again? Well, I mentioned supernovae, gamma ray bursts, also probably related to the deaths of massive stars or perhaps to the mergers of neutron stars. Again, sort of one of the end products of stellar evolution. We see flares. Here's a cartoon of flares coming off a low mass, very active star. We see novae, which again are kind of related to the endpoint of stars' lives and the accretion of gas onto it sort of on stellar scales. And we also see, more recently, what we call tidal disruptions, which I'm going to get to in just a second. But here's an image from some Berkeley folks, from Josh Bloom and Mariam Mojaz, who's now in New York. And you see, actually, they were pretty lucky here. They were monitoring this galaxy. They saw a supernova go off, and then they monitored for a little bit longer, and they saw a second supernova go off in the same object. As far as I know, that's the only time that we've seen that. But it's some pretty cool observations. There was another question.
What's a guest star?
Well, a guest star was the term that the Chinese used to say a new star that had appeared, and we now understand that it was a supernova, essentially, by going back and looking at those, looking in the same place with modern telescopes. So again, thinking about variability and thinking about sort of matching the timescales that we're observing onto the timescales of interest in the objects that we're looking at, what are those timescales as concerns black holes? Well, here's some observations of what we now know to be a black hole, actually going back to 1880, before we even knew that black holes existed. So this is kind of cool, but these are from optical plates, basically, observations that were taken over 100 years ago, that we've then been able to go back and say, okay, there was this thing that was changing in brightness. It's getting brighter and fainter and brighter and fainter. And although it's kind of hard to tell from this plot on the left, there's a periodicity here that's about 12 years. And it's now thought basically that what we're seeing here is, first of all, this 18 billion solar mass black hole with the accretion disk around it. But then there's a second 100 million solar mass black hole on a 12-year orbit here that's plunging in and out of the disk around the secondary, or in the primary, I guess, here, and causing these flares as accretion takes place onto the second black hole here. So, that's an example here where, 100-year timescale is interesting, but actually a lot of the stuff that's going on in the accretion disk is on timescales of days to weeks to months to years. Basically, how long does it take light to cross? How long does it take sound to cross? How long does it take material to free fall in? How long does it take to heat or cool the gas on these kind of scales? And so these are accessible to the scales of a research project or certainly a research career. And so, this is an area of some interest now. So how do we probe these kind of time scales? Well, one way is to just do big surveys of the sky, and a lot of the work that is being done now in sort of building these next generation telescopes is focusing on these real kind of optically fast, wide field of view telescopes with big cameras that are surveying vast swaths of the sky, sometimes the whole sky, every night, essentially, to quite faint sensitivities. You see on the left a computer rendering of the Large Synoptic Survey Telescope, which is going to be coming online towards the end of this decade. There's a little kind of computer guy for scale here, so you can see there's a pretty big primary mirror on here, but it's also pretty kind of short and stubby optically. And on the right is one of the dishes of the Allen Telescope array with billionaire Paul Allen for scale, who kindly helped fund the telescope. And you can see again that the scale, the design of these telescopes is pretty similar. Okay, they're stubby, they're wide field of view, they're optically fast, and so they're really good at surveying large areas of the sky. Here is me and Casey in here. She's still coming around that side. You might have seen Casey on the way in here. There's Casey up at the ATA, and some of our other colleagues here working on commissioning the telescope. So it was a joint effort between Berkeley and the SETI Institute down in Mountain View. Unfortunately, because of the sort of terrible funding climate for research in astronomy, UC Berkeley had to pull out. The SETI Institute is still operating, actually with the US Air Force, who are interested in tracking space debris, what they call space situational awareness. So there's still work going on up at the ATA, but what I'm going to show you is some of the work that we did during basically this 4-year period from 2007 to 11, and then some sort of further data analysis and publishing of papers beyond that. So the ATA has 42 6-meter antennas. The plan was to expand this up to 350, but again, when it became clear that the money wasn't going to materialize for that, then the telescope became sort of more of a technology demonstrator for some of the other big telescopes that are going to be built elsewhere in the world over the next few years. And this new design, I alluded to this earlier about replacing steel with silicon. It's called LNSD, or a large number of small diameter dishes. And so instead of building just giant metal dishes, you just build a large number of kind of smaller, cheaper dishes and then combine them together with a supercomputer basically at the back end. And for those of you that are interested, some more kind of technical aspects of it here, but it can operate in kind of quite a wide range of the radio frequency spectrum. So I mentioned these wide-field radio surveys. Again, you see on the left here the 700 square degree survey that we did with about 11 different epochs, 11 visits basically to this field to see whether we're seeing variability of any of these thousands of feeding black holes that you're seeing in here, the little black dots. And then on the right, a smaller field where we had more observations, going into the hundreds of observations here, basically just going back day after day and seeing, okay, did any of these things change? And this was called the pi gigahertz sky survey, because it was at 3.14 gigahertz, so we call it PIGS, which is a little bit silly, but you know, that's what we came up with. And you're seeing here, again, that same field that you just saw, but now as an animation where you're seeing kind of things flickering. You're actually seeing sort of background noise kind of coming up and going here. These aren't real sources that are out here, it's just that the sensitivity of the telescope is kind of changing a little bit depending on what the conditions are like for the observations day after day. But you're seeing, you know, maybe some variability in some of these objects. It's difficult to kind of disentangle what's the real variability and what is just kind of calibration of the telescope, and that's what we spent a lot of time doing, basically trying to figure this out. So you could take any one of these individual objects and basically plot over time, okay, how bright does it appear? Again, I should add that all of these are actively feeding black holes, basically, so that's why we're interested in them. It's radio emission from the stuff that is either spiraling in or shooting out of the black holes at the centers of distant galaxies. And so we want to see, is that changing over time? Are they just sort of heating at a constant rate, or is it going up and down? And even if it is going up and down, then is that connecting to the outflows in a similar way where, you know, the material falling in, the material falling out obviously know about each other, but do we see those kind of variations on the same kind of timescales? And so can we figure out sort of the physics and the, you know, the dynamics basically of that central engine? And so by pulling out sort of, again, this sort of light curve basically for one of these objects, you get something that looks like this. Actually, we're observing in 2 different frequencies at once here, and you see, you know, it goes up and down a little bit, but these are the kind of uncertainties on the measurements, and this thing is not really varying dramatically relative to kind of its long-term average background level. This is just an example of one of the sources from this field here. So we've got these 2 frequencies of observations. We can say, okay, well, do we see the same thing at both of those frequencies? Essentially, that's what I'm plotting here. How variable do these sources appear in the 2 frequency bands? And a straight line says just as variable as each other, basically, in those 2 bands. What we see here on the right is, okay, how big is that variability? There's more variability moving to the right, and then it's more significantly detected moving up here. And so, you know, there's things that look like they're pretty variable here, but we're not very confident that they are. Essentially, is what you're saying with stuff down here. And then there's things that don't look like they're so variable, but we're pretty confident that we measured them well, that are up in the top left here. And so sort of doing the math on this basically gives us a way to disentangle, okay, is this variability that we're seeing real, and have we detected it confidently or not? And again, it's kind of early days here, because there aren't really very many sources sort of up here where we can say, yes, we measured these really well. We can kind of plot out basically how the accretion around these black holes is varying. For those that we do measure well, we can say, okay, well, is there a lot of variability on short time scales? Is there more variability on long time scales? And we can kind of decompose that by, again, using some more math. And what you see here where it's kind of flat, basically, it's saying that even on long time scales, on time scales of 100 days in this case, so the length of the observations compared to short time scales of about 1 day, they're kind of equally variable here. So it's sort of just like a for those of you who know kind of signal processing or whatever, it's a white noise process where the variability is the same on all of those scales. It's kind of chaotic, it's noisy, it's kind of like the sort of that you get when your hi-fi speakers aren't plugged in or whatever. It's just variable, kind of static, basically. For this object, you see it kind of starts to turn up at long time scale, so this is a hint here that there's something going on, maybe kind of on a 100-day time scale, or maybe it's even going up further here, so maybe we're seeing kind of irregularities in the accretion disk here, or something that's connecting to these outflowing jets. And so we really want to study kind of more of these objects and get more of these statistics in order to get kind of, an ensemble of objects and an understanding of how black holes behave, when we study hundreds of them. Yeah.
Is it possible it's related to the rotation of the black hole itself?
Related to the rotation of the black hole itself?
Yeah.
Yeah, I mean, we think actually that the launching of those jets is probably related to, first of all, the spin of the black hole, and secondly, the accretion rate, basically the fraction of, when you're trying to feed, the monster, when you're trying to feed Cookie Monster, how many cookies can you shove in kind of thing? I mean, there comes a point where, you might as well give up, because it's like feeding a baby, I guess, as well. You've got to kind of get it at the right rate so that most of it's going in. And if you try and throw a lot in at once, then you're going to get a bigger mess. Okay, and so we see that with the black holes too, basically. The gas that's trying to fall in at kind of low levels, basically, more of it is making it in there, but also it's more likely to launch these jets at low levels, and then when you kind of shove a whole bunch in, then it's sort of disrupting the jet formation probably, and actually you get more kind of winds and outflows that are more spherical, basically. Again, very poorly understood, and that's kind of why we need to do this, basically, to figure it out a little bit more. If some of you were watching this closely, you'll have seen transient sources here. I mentioned, transient sources before, and it's actually going to be somewhere around here. There it was. Just kind of pops up and then went away again. But really, this is kind of, I like to think of it as like a grumpy cat transient, basically. It just kind of popped up and went away. What was that? You saw the cat in the earlier picture. We'd really like to see something twice in the same place to be sure that it really was real and not just sort of some problem with our equipment. And so we went digging a little bit deeper into this, and what we found is that this little source that pops up here, come on. There it is. That was actually this source that kind of ended up with a ghost image over here, because the telescope was pointing in the wrong place for like 10 seconds or something before it slewed onto its next target. And so, we got a little bit of this source in the wrong place, basically, and then we got on target, and then everything looked fine. And so really, the regime that we're operating in right now is sort of a regime of kind of weird bugs with the system kind of thing, where you don't expect to see things like that very often. In hundreds of observations, we only saw one of these things. But where you have these glitches, we have more glitches than we have real events right now in terms of these transient events in radio astronomy. So we've got to be really careful about making sure that the things that we're seeing are real kind of flares, let's say, for example, as opposed to problems with the telescope or with the calibration. So what kind of things might these be? I mean, certainly sort of it would be nice to see something that popped up and was quite bright and then kind of gradually decayed away again. And if we saw that, and if that light curve had a specific shape, then we could be fairly confident that we were seeing a black hole snacking on a star. So I've talked a little bit about kind of the black holes gorging themselves on gas, but what about if they just want a little snack? Here's a little cartoon. So see the black hole against the background here, see the star that happens to wander too close, and the gravity of the black hole is pulling on one side of the star more than it's pulling on the other side of the star. It's kind of like the tides of the moon on the Earth. Basically, the reason why we have tides is because the gravity of the moon on one side is a little bit stronger than the gravity on the other side that's further away. And you see the same thing with the star here. That's what we call tidally disrupted. In other words, that the sort of gradient in the gravity of the black hole is stretching and squishing and tearing the star, and about half of the mass of the star falls in and launches the secretion disk and the jet that's associated with it that looks pretty similar to the earlier cartoons that I was showing you of the active galactic nuclei. Just 1 second. And the other half leaves the system basically and never makes it into the black hole. Yeah.
So the jets are not constant. They change all the time?
In this case, That's right, yeah. In the cases that I was showing you before, where the black hole is sort of constantly feeding, and really those changes in net accretion, we think probably only take place on millions or tens of millions of years, basically when the black hole turns on, and then when it turns off again. That's probably sort of a 10 or even hundreds of millions of year time scale kind of process.
And how far out do those jets go, and what is the effect if something passes through?
The jets go out millions of light years into intergalactic space, and as I showed in an earlier slide, basically they're kind of blowing bubbles in surrounding gas, potentially triggering the birth of new stars nearby in that gas. Potentially if one of them kind of hit a nearby galaxy in which there were planets hosting life, then it could strip off the ozone layer from the planets. I mean, it kind of depends. That's a little bit more speculative, but these things, the actively accreting black holes, the AGNs, are a part of the life cycle, if you like, of most major galaxies. So at some point in their history, certainly big galaxies probably had a phase where their black hole lit up like that. But what we're seeing here is just kind of a quiescent black hole, which most of them are. Like 99% of the supermassive black holes are really just sitting there not doing very much. And every once in a while, probably about once every 10,000 years in an average galaxy, a star wanders a little bit too close, like those ones that I was showing you, around our own Milky Way's black hole. They weren't getting too close, they managed to get out again, but every once in a while you get kind of a hole in one, basically, and this is what happens. There was another question, I think.
So there's this point in this animation where the star is kind of getting distorted, and then all of a sudden, boom, there's like a big flash. And, is that an artifact of the animation, or is there something real about that?
Well, I mean, actually tearing a star apart is a pretty violent process.
So if you watch it right here, ready, distorting, and then boom.
That's a good question. I mean, I'd have to go back and read the papers on exactly what's happening, but you've got a star that's happily kind of running a fusion reactor, and it's cold out basically, and then you're tearing that fusion reactor apart, so it's probably something to do, if you thought like Fukushima was bad, then try, tearing a star apart. Yeah.
And is it a funnel that's always getting from one direction, getting stars from a certain direction?
Probably not, no. I mean, it's just, there are stars on various orbits in the interior regions of the galaxies.
So it could come in at any angle to the pole.
Yes.
It's more like, say, a ball that has a magnet of things around it.
Yeah, and that's actually a good point, because, there may be changes in the phenomena that we see, at least at kind of some small level, depending on whether, if the black hole's rotating, is the star coming in aligned with the rotation of the black hole, or counter to that rotation, and we do think that with more precise observations, we'd be able to tell the difference between those. So this was really kind of,
Did you say that a star can go into a black hole and it can't come out?
No, I said in this case, so, and this is one word that is, a British immigrant to the United States that I have terrible trouble pronouncing. One of them is banana, and the other one is half. And people don't understand what I'm saying, they go into the coffee store, where's the half and half? So half a pound of roast beef at the butcher's counter or whatever. Half of the star falls in, and the other half kind of coasts on out. But yeah, none of it actually that goes over the event horizon. Excuse my mangling of my mother tongue. So, cartoon here again. This is something that was predicted by a famous astronomer called Martin Rees back in 1988, but it hadn't been seen until a couple of years back when the Swift satellite that I mentioned before saw this bright flare. And actually, what you're seeing, I think, here is ultraviolet and optical in white and purple, and then X-ray observations in. I should read my notes here, they're going off the bottom of the slide. The X-ray, I think, is in blue, presumably, or red. And so you're seeing a flare from, that was detected by the Swift satellite here. So before, I don't have a before image here, but suddenly there's this very bright thing, if you like, a guest star that appeared, although in this case it wasn't, well, it was related to a star, because it's now understood that this was one of these tidal disruption events. It was a star being swallowed by a black hole. And the reason why we know that is because we followed the light. We, I say, the research team that did this followed the light curve, followed the brightening of this event. So after the trigger back here, basically, from the gamma ray observations, it was monitored carefully in radio using the very large array at 2 frequencies. It got quite a bit brighter again here on the log scale, so it's sort of a few hundred times brighter than it was initially over a period of about a year, basically months to years, and then it fades off. It's predicted to fade off. These stars, the actual observations, and then sort of on a 10-year time scale up to a 100-year time scale, it's predicted that it's going to fade off back into undetectability again. And so this was the first one of these that had been seen, the first tidal disruption event, the first black hole actually just snapping on a star going past. Shortly thereafter, another one was seen by a group led by Brad Sanko, who was in Berkeley Astronomy until recently. And here you do have a before picture, and then you have an after picture, and then you have kind of a zoom in here that's showing basically where all of the observations of the different wavelengths aligned. And again, this was tracked over time, the flare was tracked over time. And it's understood again that this is another tidal disruption event. And so we're starting to understand the physics of these, and we're also starting to understand the statistics of the populations, how many there are, basically, as I alluded to, about 1 every 10,000 years per average galaxy, something like that. Yes?
Which one again there is having the tidal disruption event?
Well, you don't actually even see the galaxy beforehand, in this relatively shallow observation from the Sloan Digital Sky Survey in the optical, and then suddenly it's marked here by. So this is, again, it's a negative image. You're seeing this little black dot is actually a bright spot, basically, that suddenly appeared at the position where the Swift satellite had seen its gamma ray trigger, which I think is probably the cross there. So here's zoomed in kind of after the fact with the Keck telescope, and I think that's the radio position there, the white circle. So again, all the observations are pointing to this consistent picture, that this was another star that was being swallowed. I'm kind of running a little bit short of time. I'll scoot through the next slides a little bit faster. I may just pass over some of these, but this is some work that was done where, again, kind of a bunch of these transient candidates were seen just in a single epoch of observations. So this was 944 observations over a period of years of a calibration field for the very large array. And some of these, the squares and triangles and diamonds, mark these sources that were only seen to just appear once and then go away again. And so there was some interest. This was work by my boss here at Berkeley, Jeff Barrow, and we went back to follow this up. Another group followed it up first and said, okay, we're going to do some deep optical imaging and see, are they in galaxies? The positions of these radio transient sources, essentially no galaxies were seen. I mean, there's one here where it's like, okay, well, that's pretty close. Is that associated with that? We kind of have to figure it out. I'm going to gloss over this, but you can ask me sort of some more later if you're interested. We went back a little bit later and did some X-ray observations. So you're seeing this kind of complicated picture here that's showing in white all of the sources that we saw in X-rays, in green the sources from the radio observations, and in this kind of color and red image in the background observations from optical. And so you're trying to make sense of all this and say, okay, which of these things are associated with which? Are these transients really associated with X-ray sources, for example, which might tell us that it was related to a black hole that was feeding and sort of, basically flared in X-rays and flared in the radio, or is still feeding and emitting X-rays, but then flared at some point in the past. And so we're trying to kind of disentangle all this. I'm going to gloss over this. It's kind of too much detail to get into right now, but we found that there was one of them which seemed to be associated with an active galactic nucleus in the sort of relatively distant universe. And we did that by doing these multi-wavelength observations and essentially kind of fitting templates to those observations to figure out how far away this thing was and what it is. And it is indeed one of these active galactic nuclei. But then kind of the weird thing is that, you look at it and there's this big offset here. We would expect that if this was a flare, then it would be aligned with the X-ray source at the center of the galaxy. It also, if this was a flare and it was at this distance, then it was a really huge flare that doesn't really fit any of the models of the black hole tidal disruptions or this kind of thing, or even of a supernova or a gamma ray burst. And so it's still, again, it's early days and it's confusing. And the X-ray source we think is real. The radio source, we're understanding with further analysis that, again, some of these radio sources that we're seeing were kind of associated with glitches in some of the earlier observations. Some of them are kind of maybe not as significant as they were initially thought by those first authors. Some of them are definitely real, and the reason why we know that is because actually if you were to just kind of pair up, if you were to pair up radio and X-ray sources here, if you just kind of threw them all down on the table here, if you threw down red balls and black balls on the table and they were just randomly distributed, then you wouldn't expect to find that they were paired up in any sort of statistically significant way. And so we can do that test with these, and we find that actually the X-ray and radio sources are closer to each other on average than we would expect them to be if they were just scattered throughout the image. And that tells us that there is some association there, but it doesn't tell us specifically which X-ray sources and which radio sources are associated with each other. And that's essentially what I have, what I have here. What you would see if they were random, and there's a little bit of kind of clustering basically above and beyond the randomness. But again, some of these are just kind of weird. We only saw them once. They're possibly not real. We need bigger surveys, we need more data, we need to do more wide field, long-term imaging in the radio.
Is that your cat?
No, that's Grumpy Cat. If you're not familiar with Grumpy Cat, then you should Google her, because she's a internet phenomenon. So, moving from the very large array to, the ATA, seeing a much larger field of the sky, a little nod to the SETI Institute here. Probably wouldn't appreciate that if I'm doing serious science that is searching for signals from extraterrestrial civilizations that probably don't actually look like ET from the movies. Okay, I'm going to go through. I'm going to move on to the cannibalism, galactic cannibalism and black hole cannibalism. And here's a picture of two merging galaxies. It's essentially what I'm getting at. They're kind of eating each other, basically. This is a real image from the Hubble Space Telescope. And we see a bunch of these when we look out there in the universe. Here are some more merging galaxies, and actually these, again, we're talking about the SWIFT satellite, the gamma ray satellite, that's detecting an excess of these actively feeding black holes in these merging galaxies, which is telling you essentially that the mergers are helping feed the black holes, probably by more gas from these incoming galaxies getting stirred up and getting sort of sent down into the inner regions of the galaxy where they're managing to make the black hole grow. But this is just this kind of steady, again, kind of AGN accretion. Just one second. And this is from some work that I did with some collaborators out at Livermore, where we paired up a radio survey. So essentially you're counting the number of active galactic nuclei as a function of how big the galaxy is, and what you see is that bigger galaxies are more likely to have active galactic nuclei, going up from close to, so a few percent up to about 30% of the most massive galaxies have these actively feeding black holes. And then what you see here, so on average that's the black line, but then the blue line and the red line show the difference between galaxies that are found in just kind of relatively less dense environments and galaxies that are found in more dense environments where they have more close companions. They're more likely to be in galaxy clusters, richer galaxy clusters here. So just splitting them kind of into these two bins, and you see that even for a galaxy of a given size, if it finds itself with more close companions, it's more likely to have an active galactic nucleus at the center. And so again, that kind of influencing the stirring up of the gas and how much of it gets down there. Sorry, there was a...
So when two galaxies merge, presumably they have two massive black holes, and do those two massive black holes merge?
We think they do. So black holes will sink down to the center. In some cases, they're going to get, kind of one of them will get scattered out of the galaxy, but in many cases we do think that they will merge. Simulations from Chris Hensey down at NASA Ames in Mountain View. I think this is kind of a cartoon view of a simulation, but what you're seeing here is gravity waves spreading out through space-time as the black holes merge. These are hugely violent events. And actually this room right now is saturated with gravity waves from the mergers of supermassive black holes, which is kind of cool, because these are going on all over the place in the universe. Space-time itself is basically ringing like a bell with the waves that are coming out, emanating from these kind of systems that are passing through us, and actually they're stretching and compressing this room as we sit here in your bodies and all the atoms in your bodies. except only by a really minuscule amount, to the extent that I think it's sort of 1 part in like 10 to the 15 or something. It's smaller than the diameter of an atom on a scale of several kilometers, and that's why these things are really difficult to detect. There's a couple of experiments that are aiming to do this, yeah.
Well, as long as we're on that topic, black hole can never get too big. I mean, they just can get bigger and bigger and bigger as far as we theorize.
Can a black hole get bigger and bigger and bigger? I mean, we do see they sort of cut off at some stage, and that's probably just related to how long they've had over the history of the universe to grow at the maximum rate that they could grow. But yeah, there's no reason, I don't think, theoretically, why they couldn't get bigger. Yeah.
You say bigger, does that mean more massive? It doesn't really mean bigger in dimension.
It means both. I mean, the black hole itself, the singularity there at the center, basically has no size, but the event horizon, the size of the event horizon just relates to the mass. Actually, you put more mass in, and the event horizon gets a little bit bigger. Yeah.
Do they all rotate? What happens if they join together and they're rotating in the same direction, the same plane, or they're rotating in opposite directions in the plane?
Right. Again, good question. And you know, we've not seen this specific kind of late stage spiraling in. There are a lot of people who've worked a lot on the general relativistic equations that tell you how this works, and yes, you do see a difference. You see a different, I mean, basically what I'm getting to is there's observational signatures of this, and the flare that you would see from this is different depending on whether they're co-rotating or counter-rotating, so yeah, very good question. Okay, so how do we detect these ripples? Well, there are some folks that are looking at pulsars, which are spinning neutron stars that are kind of beaming out radio waves that we see essentially like a lighthouse effect of the Earth if the beam happens to kind of pass by. Some of these are rotating, they're sort of the corpses of stars basically, they're rotating, some of them hundreds of times a second. So imagine sort of something, you know, the mass of a star basically the size of the Bay Area that's spinning hundreds of times a second. So these are really powerful kind of objects too. They're beaming out these radio waves. I won't get into kind of the physics of pulsar emission, but there are people here at Berkeley that work on this kind of stuff. But what you're seeing here again in this kind of cartoony picture is somewhere off here in the distant universe, there's a merging pair of supermassive black holes. These ripples are coming through space-time and basically kind of distorting the pulses from these pulsars as they pass by. And so if you could time these things very precisely, the pulsars are very regular clocks, and if you can time them at Earth, and if you see that timing signal change a little bit for particular pulsars in a particular direction, and if you can do that for a whole bunch of pulsars, then essentially you can see the ripples in space-time that are coming from the supermassive black holes. And there's actually a race on to be the first to detect gravitational waves. There are some groups that are doing this with radio observations. I'm not involved in this work myself, but there are some groups that are monitoring pulsars with radio observations. There are also groups that have giant lasers that are several kilometers long, and they're looking for changes in basically the length of that laser beam as the gravitational waves pass through. And actually, those experiments are sensitive more to the mergers of smaller black holes. These pulsar timing experiments are sensitive to the mergers of supermassive black holes. And the prediction is that as these experiments are going on, that sometime in the next few years, essentially by the end of this decade, if we haven't detected these using one or other method, then there's probably something wrong with our understanding of relativity or the physics of pulsar emission or black hole mergers or something, and so that really will be kind of back to the drawing board. Very briefly, I'm working with some folks at the University of Wisconsin in Milwaukee to look for the signatures of the kind of late stage in-spiraling these black holes. So before they merge, maybe sort of hundreds of years before they merge, where you're seeing a simulation that we did to show kind of how the radio emission might change, getting fainter and brighter over time. So there's a lot of scatter in here, but you can see that there's this underlying sort of wave shape here, basically, that we hope with enough of these objects to be able to detect. So we're simulating right now how many of these will be seen in these big next generation surveys. So talking about next generation surveys, these large surveys will see obviously a lot of just the standard accretion that we've been seeing so far. They'll see more of these tidal disruption events, and they'll see the end spirals of these supermassive black holes. There's a whole bunch of acronyms here with some of the telescopes that are going to be coming online over the next decade. So if we can get these right, the Murchison Wide Field Array, the Long Wavelength Array, the Australian Square Kilometre Array, Pathfinder, the Low Frequency Array. This is the Karoo Array telescope, and they made it bigger and bigger in Afrikaans is meer, so it's more Karoo Array radio telescope or meer. This is the Westerbork Synthesis Radio Telescope in the Netherlands, and they have a new detector on that. And ultimately, we're heading towards the square kilometer array in the radio, which I'll mention briefly in a second. And it's really kind of multi-wavelength. So these are all radio telescopes. We're also incorporating X-ray and gamma ray and optical and infrared, and all of these telescopes working together to study black hole growth. And multi-messenger as well, which essentially what I'm talking about there is gravitational wave detection, things that aren't kind of ordinary light, but are actually sort of other signals from these objects. So I showed you the VLA field of view relative to the ATA. Here's the Australian SKA Pathfinder, and here is the Murchison Wide Field Array, which is essentially kind of like LOFAR that I showed you before, just a bunch of kind of radio aerials, except instead of being in a muddy field, they're in the outback in Western Australia. And so this has a really big field of view. You can see a lot of the sky. Skipping through, there's an ASCAP antenna. It's going to survey basically most of the visible sky every day, 230 times as fast as the ATA did, with 10 times better resolution. It should see about 60 new tidal disruptions, which it will then monitor over time, every sort of 10 daily visits, basically, plus about 20 radio supernovae and a handful of gamma ray bursts, maybe a few tens of these inspiraling black holes, and 250,000 of these actively feeding radio AGNs that will monitor every day. So this is real kind of revolutionary stuff if ASCAP works, according to the design specifications. The MWA is already online. Here it is again, kind of dipoles in the outback. This is a view from a plane. I won't get into this plot here on the left, but we're basically kind of pushing down in sensitivity and surveying larger areas, which enables us to really explore kind of regions of kind of area of space and time and sensitivity that we haven't been able to look at before. And so sort of 10 years and on, we're aiming towards the square kilometer array, a simulation from some guys in Australia. This is now in the early stages of construction in Western Australia and in South Africa. And it's going to be basically thousands of dishes and thousands of these dipole antennas that are really going to kind of transform our understanding of how black holes grow. So I'm going to kind of skip over these. I'm going to finish up and then I'll take some questions. I'm just going to skip over these questions, but we want to know how do gas and stars basically get into the central regions of galaxies and into the black holes? How do these supermassive black holes emerge? How does that connect to the jets that are flowing out? Why are some black holes just sort of sitting there and not doing very much, and others are steadily accreting, others are flaring as they're swallowing stars, or the accretion rate is changing? When you do a census of black holes, how do they relate to the galaxies that they find themselves in? And how can we make use of all of these different wavelengths and also of the signals from, particularly from gravitational waves, to really understand not just the black holes that are showing up in these surveys, but also other transient and variable sources, supernovae, and maybe, who knows what else might crop up here. So to just kind of put up the final slide, basically I talked a little bit about black holes snacking. I've talked a little bit about black holes gorging on gas, which really is mostly what we see right now. And I talked about them cannibalizing each other. And I hope that I've left you with kind of a flavor of where this field of research is going to go during the next few years. So stay tuned. Thanks.
Very simple question. Those facilities, are they in the southern hemisphere to minimize radio noise?
The question is, were those facilities that I showed in the southern hemisphere because there's not much radio noise, or is there some other reason? And actually, by and large, there's a lot of open space in Western Australia and in the Karoo in South Africa, the Karoo Desert. I did show you the one that was built in the Netherlands, and you might think, well, why build a radio telescope in the heart of Western Europe? And I mean, actually, that was a question that came up sort of when that was reviewed, but really it was sort of a political decision. It was EU money, it was Dutch money, and their collaborators, and they wanted it to be built there. It means it's not the ideal site. It's kind of like optical astronomy. you know, in the UK, the Royal Greenwich Observatory, I mean, now it's sort of in the suburbs of London, they moved it out to towards the south coast where there was less light pollution, but the English weather's still terrible. But, you know, at least it was kind of a short drive for the astronomers to get out there. Now, you know, all of that takes place in Hawaii, you know, on the tops of remote tropical mountains.
How about space-based observations?
Space-based is really important for things like the X-rays, so I showed the SWIFT satellite because the X-rays don't penetrate Earth's atmosphere. For radio observations, first of all, the radio observations will penetrate the Earth's atmosphere. Secondly, it's difficult to get all that hardware up there, you know, thousands of antennas basically up into space. Some people have explored, you know, should we be doing more of that? There's talk of putting radio telescopes on the far side of the moon where they'd be shielded by thousands of kilometers of rock from your garage door opener and your cell phone. But what we're doing basically now a lot with the more modern radio telescopes is just focusing on measuring kind of across a range of channels. You know, if you dial through your radio dial, if you're driving out through, you know, the remote outback, if you're looking for the FM stations, and actually really the MWA is operating in and around the FM band. And so imagine kind of dialing through, you wouldn't pick up very much. Actually what they do see, which is kind of neat, is they see reflections of FM stations from distant towns off both the moon and the International Space Station as it goes overhead, so they can track these things as they move, which is kind of a cool sort of byproduct. But mostly that radio dial is kind of empty and just full of static. You know, in the Netherlands, obviously that's very different. But what could you do to get rid of that? Well, you just need to be able to tune pretty finely and ignore the channels where you've got a lot of radio noise and focus on the ones where it's relatively quiet. Yeah.
Yes. So you talked mostly about radio and a little bit about X-ray. What is available in other parts of the spectrum, visible, infrared, ultraviolet, etc.?
Right, good question. A lot. I mean, you know, these active black holes, certainly quasars, which is a term that's sort of used interchangeably really with AGNs, although they essentially refer to the same thing broadly, were first discovered, or you know, first understood really with the help of optical observations, particularly optical spectroscopy, splitting the light up into its constituent parts. So when you have an object that you want to know whether it's an AGN or not, one way is to confirm it with optical spectroscopy. But you know, part of the problem is so I said the sky is full of galaxies. You know, find the AGN in this picture, as opposed to in this picture where everything in there is an AGN. You know, it's easier in radio.
So there's much less interference in the radio spectrum than in visible.
I mean, it's not so much interference, it's just that there's a lot more going on. Actually, it's mostly kind of starlight here. You know, the optical is very good for studying starlight. It's also good for studying hot gas that's falling into black holes, but stars don't emit as much in the radio as AGNs do, whereas in the optical, you know, disentangling those two things is a little more difficult. It can be done. I mean, I don't mean to say that this is useless. It's very useful, but and it's also kind of not really an area that I focus on as much. I'm more of a radio kind of guy. Yeah.
I was curious about also the spectrum that you're using for the Allen telescope. You know, how you selected those particular frequencies that at least the picture showed 11 point something gigahertz. How those are chosen and what that represents, and also, are you looking at a specific section of the sky showing the same data over a period?
Right. They were chosen partly to avoid radio frequency interference. We actually found kind of a sweet spot around 3 gigahertz where there wasn't kind of much pollution, basically. Partly for sort of reasons of how bright these objects appear at different frequencies. But it was also kind of a, you know, I don't want to call it a fishing expedition because we get dinged by the National Science Foundation and people like that if we propose to just kind of go out there and see what we find. But let's call it a technology demonstration or you know, an initial kind of pilot study or you know, characterization search basically. And you know, nobody had looked at this before basically to look at the variability on those kind of timescales of those frequencies. So that was basically the reason.
Going back to the analogy of the Cookie Monster, so 90% of the material is just messy stuff floating around. Supposedly it will recombine into stars at a certain point?
Yeah, eventually. I mean, you know, there's a lot of gas out there in the universe, and if it gets dense enough, then some of it forms stars. there's kind of some enrichment of material that goes on. You know, the universe was initially just hydrogen and a little bit of helium, a very small sprinkling of lithium and heavier objects, and then as stars were born, particularly massive stars, they kind of process that gas into heavier elements and kind of recycle the gas through sort of several generations of stars. And the heavy elements that make up the Earth and that make up the, you know, the calcium in your bones and the iron in your blood came from massive stars and from supernova explosions. You know, this is not an original thought for me, but we're made of stardust, the stardust in our bodies. And so, you know, things are getting recycled in space all the time. As to whether any one parcel of gas is ever going to end up in a star or not, I mean, it's sort of...
Because 90% that's massive, right?
Yeah.
So is that something we can actually observe, that 90% recombining at some point? Would that be an indication of a black hole in itself?
I don't think we've seen that specifically. You know, and it's only the stuff that's going into those black holes. When you have a galaxy that is, you know, hundreds of billions of times the mass of the sun, feeding a black hole, you know, really you're only talking about sort of a solar mass per year or something like that, or maybe a little bit, you know, around that kind of ballpark, a little bit less, a little bit more, or a lot less, perhaps. But that's not very much. I mean, it's a lot of gas to throw into a black hole, but it's not very much gas in terms of the budget of gas that you have on kind of a galaxy-wide scale. So I did show, you know, I mean, talking about forming stars, you know, I did show the connection between these outflows and star formation here. But I mean, this isn't the gas that, you know, there's gas here that's falling into the black hole here, and then you know, tens of thousands of light years away, there are stars forming that are related to the jet from the black hole, but it's not the same gas, basically. Yeah.
Yeah, on the 10% of the gas that goes into the black hole, it's like protons, neutrons, electrons, and once it goes to the event horizon and it approaches the singularity, we know any idea what state of the matter
is? It's just mass at that stage, basically.
Pardon?
It's just mass at that stage, basically. I mean, all of that gets erased. There's only actually three things that you can measure about a black hole, and that's mass, charge, and spin, and everything else, all of that information just gets kind of wiped out, basically.
You don't know what's inside.
Right. Yeah.
So these galaxies that merge and then have multiple black holes, can they stay with multiple black holes for some amount of time? I mean, do you have like binary galaxies in the sense that...
Yeah, in fact, we have seen that. I didn't show pictures of that, but there are some where you see two AGNs there. You might see them as two X-ray point sources, for example, where they're both accreting. Not very many, I mean, there's a handful of those that have been seen. That's kind of earlier on in that sort of in-spiral. We want to try and catch them as they're really kind of in the late stage, and then there should be a flare that's associated with the final merger as well, but we haven't seen that yet.
Kind of a basic question. I hope it's not stupid. What causes the rotation of the black hole in the first place?
No, that's a good question. I mean, why do things rotate in space?
Right.
The other sort of, you know, opposite question to that is why would things stay still? Okay, you know, you have a cloud of gas, and I mean, especially if it's a big cloud of gas, it will be sort of unnatural for it not to be kind of slowly drifting at some level. And then what happens, like an ice skater, basically, as the gas cloud collapses, and there's a little bit of rotation, and sort of pulling its arms in, conservation of angular momentum, means that it's going to spin more and more. And that's why we see, you know, why all the planets are in a disk in the solar system, and why the sun is rotating in the same direction as most of the planets are. Essentially, it's that the cloud of gas that went to form the solar system had a little bit of a kind of drift to it, and then as it collapsed, the angular momentum basically pancakes out like pizzas out, like somebody, you know, spinning a pizza basically, and it flattens out. Same thing with the accretion disks around black holes basically, and with the black hole itself, that it's just kind of the angular momentum being conserved as the system is sort of collapsing in on itself.
And the rotation direction, probably, I guess it doesn't matter.
Yeah, I mean, you know, trying to figure out what that rotation direction is, and trying to figure out when galaxies merge. You know, there was a question earlier about what happens if they're rotating in different directions or the same direction.
They're rotating always in different directions depending on whether you're looking at it from the top or the bottom. So I guess.
Well, no, I mean, if they're both going that way, then
right. I mean, typically they're in the same plane, but if just looking at a black hole or a galaxy in isolation, it rotating clockwise on one, if you look at it from the top.
Right. But you know, are they co-rotating or counter-rotating? Is it like gears that are kind of, you know, grinding against each other, or, you know, I mean, bad analogy maybe, yeah.
Yeah, so how close do we think, you know, the closest black hole is that we've detected? And are there any significant concerns that if a black hole came too close to the solar system, there would be serious disruption?
Space is really big, and actually we have a couple of guys here from a summer program that we've been doing where we did an exercise about the scale of the solar system, and I don't know whether Darius or Boris would like to comment on how big space is, but we did a model solar system with Play-Doh, where we made the sun basically a ball 1 meter across, and the Earth is a pea on that scale, and the sun was a ball in the YMCA in downtown Berkeley. The Earth was a pea on the same SETI block. Pluto was like this tiny little speck basically up at Space Sciences Lab on the hill, and the nearest star on that scale is 15,000 miles away. And so, you know, try and get a hole-in-one golf shot from hit the Earth from that kind of distance.
So the number of black holes is so small, the odds are infinitesimal.
The number of black holes is pretty big. It's certainly smaller than the number of stars, and we know that collisions between stars don't happen very often because the space between them is so huge. And, you know, maybe there are 1% as many stars as there are, and 1% as many black holes as there are stars in the galaxy. So, you know, maybe the nearest one is hundreds or thousands of, probably hundreds of light years away, something like that. But the chances of it getting close enough to do any damage are pretty remote.
So we can stick to worrying about asteroids. We
Yeah. Yeah.
No, there's a lot of interest in this 10%, 90% thing. Well, of course, we can't observe it because, for one thing, the timescales would be too critical. There is, at least a theoretical analogy, because the dynamicists think that smaller bodies in the solar system, that Jupiter has kicked something like 10 times as many out of the solar system as have been captured.
Yeah, so sorry, what was the question?
Well, just that there's an analogy, a theoretical analogy, between the way that small objects get handled in the solar system, but eventually most of them being ejected, according to any rate to current theoretical models.
Yeah, I mean, sure. I'm not sure that that's necessarily kind of telling us that there's any sort of scaling relation or whatever.
I just detected a demand for straws, so I can't.
Let's take one more question, yeah.
Do spiral galaxies share a rotational plane, or are they at just random angles, planes?
Compared to each other?
Yeah.
They do not share a preferred rotation direction, and actually, there was some, have you heard of Galaxy Zoo? There's some of you probably have, there's a project called Galaxy Zoo where you can go and classify galaxies. You know, it's kind of free labor for the project, you know, principal investigators, but it's also kind of a fun thing to do. Like, as an amateur, basically, they show you a picture of a galaxy and they say, you know, is this a spiral, or is it an elliptic, or is it a clockwise spiral, or a counterclockwise spiral? Is it a merger? You know, and you can just go and click through. And they found actually that so long as they get like 10 classifications per galaxy from just random people that log onto their website and go through that little training thing, that it's actually more accurate than getting a grad student to do it. A lot cheaper. And you can classify, you know, thousands of these things basically. People just going through. In fact, their most successful galaxy classifier, I think they figured out that since the project launched, if he had been, and it was a he, if he had been classifying galaxies at a rate of kind of 1 every 4 or 5 seconds for the lifetime of the project, then he'd been doing this like 40 hours a week, basically non-stop for a couple of years. They were grateful for his contribution. I think he was quite a good classifier. But what they found basically was, initially, was some thought that it appeared that galaxies in one part of the sky had a slight tendency to be more counterclockwise than galaxies and the opposite side of the sky. And like, this is really weird. I mean, does the universe have a preferred direction, preferred axis? They dug into this a little bit more, and I think they basically solved this by flipping the images of the galaxies around and having people classify them again. And they found, I think, I think I'm remembering this correctly, that right-handed people have a slight preference to kind of misidentify when they're not sure. Yeah, I guess that's correct. I think it's probably leave it at that if some of you, we're at 12:30 and probably want to take off, but thanks a lot.